There we go. Hello, everybody. You might notice this is right after class. Perfect time. I decided to make an entirely new video to make sure I have everything perfectly clear in the best way that I can. So here we go. This is all of refraction that we've studied so far, all in one. So the most important thing is, first of all, to understand refraction as a cause and effect. And the concept is this. So I might approach this a little differently than I did in class, just to get the information down. But the logical flow, I did in class a little more succinctly. So the concept is this. The velocity depends on the medium. And at some point, I'm going to, specifically next week, ask you guys to use these equations, right? And I actually think it's supposed to be gamma, not mu. Sorry if that's confusing. That adiabatic constant I do not mean to be confusing. For a gas, we'll bring that up later though. But I'll just give you these values for now, just until we like solidify that concept when we do thermo. Either way, Bruck modulus over density, you guys, I think, understand a little bit, at least more than zero. We can use that one. Velocity depends on the medium. So if I go from, say, a heavy gas to a light gas, well, what does that mean? It means it goes faster. So this is slower, this is faster, right? So what happens is the frequency is constant, and if we change mediums, which is the whole point of refraction, I'm kind of putting these two together. Change mediums, V changes, F is constant, so lambda changes, right? And V is directly proportional to lambda, or should I say lambda is directly proportional to V, because lambda is the result. The wavelength is never the cause. You can never cause a wavelength on purpose. You can only cause it by knowing that a certain velocity and frequency will create. Frequency is the input. Velocity is the medium. That's the physics of waves. So the wavelength changes from heavy to light. The wavelengths will get farther apart. So we can draw that as close wavelengths to far wavelengths. Now, remember, these are wave fronts. So this is lambda, and we have the ray representing the velocity v1, and here we have the ray v2, right? The ray is always perpendicular to the wavefront. Now, the wavefronts are what are the geometric way to look at the cause of refraction. But the ray is what we end up drawing, right? So from this, the chain of logic is, okay, because the wavelength changes, the angle changes. And here's how it changes. Faster is a larger angle. Slower is a smaller angle. And I'm going to show that on the next slide. This is the concept, cause and effect, right? If it goes straight in, it just comes straight out. But if it comes in at an angle, say we go from slow, like a heavy medium, to fast, this is some V2 and V1, then what happens is that the wavelengths have to align like this, because the compressions need to meet here. This is the input, remember? So this is wiggling back and forth. So this is going to wiggle this back and forth. So the new wave that propagates through, where did this wave came from? It came from back here, which came from another wavefront coming in from the top medium. So this compression has to match with this compression here because it's the input, it's what's causing it. So this is lambda 1, this is lambda 2, and to fit the wavelengths in, see what I mean? The wavelengths, the wavefronts show that the angle must change. It's got to change. So the ray is perpendicular, right? It goes like that. And here the new ray is where? It's like that. And what we do is we draw what's called the normal line. And we look at the angle with respect to the normal line, theta 1 and theta 2. The angle is between the ray and the normal line. So when you're drawing this, by the way, pause the video to take this in. I'm going to go pretty quickly now just to be efficient. When we do this, how do you do refraction? Well, here's my little step-by-step. Step 1 is draw the normal. It's perpendicular to the surface, to the boundary. Nice little perpendicular sign there, right? Draw the normal line to the ray meets the normal at the boundary. Right? We call that theta 1. That's the incident angle. I think I switched my 2 and 3 in class. Same information, just delivered a little differently. The ray meets the normal at the boundary. This is theta 1, the incident angle. This is just meant to be squiggles like parentheses or brackets. Let's draw it. Here's my boundary. Here's the normal line. Here's another boundary. Here's a normal line. Here's a normal line. Here's a normal line. Here's a normal line. Why? Perpendicular to the surface at the boundary at that specific point. So if I have rays coming in here, this is theta 1. This is theta 1 equals 0 because it's right at the normal line. This is theta 1 and this is theta 1. We call that the incident angle. All of these will then have a theta 2. Now here's the concept. I'll write it again. Concept. Right? If you go faster to slower, right? Slower means what? Wavelength decreases, which means angle decreases toward the normal line. And then the opposite is true, right? Slower to faster, right? And I want you guys to be able to follow this logic, not just like rewrite it. I want you to apply it. And that's what your homework's for, right? You're going to apply this to certain geometries. You're going to think about it. But obviously, we want to know where it comes from. It comes from these wavefronts, right? It comes from this chain of logic here, right? Velocity depends on the medium, which changes the wavelength, which changes the angle. So here, faster means wavelength increases, which means they have to, that's this situation, they have to slow to fast, it's got to speed up. To speed up, it's got to spread out. To spread out, the angle has to increase. Rewind the video if you want to hear me say that a little slower. You can even make it go half speed or double speed. I challenge you. Theta 1 is less than theta 2, right? So here toward normal, theta 1, the incident here is faster, so it's bigger, right? Ooh, there we go. It's bigger than theta 2. Right, faster to slower means it does this. Faster, slower. Theta 1, theta 2. Slower to faster, lambda increases, so theta increases away from normal. Perfect. And we get that theta 2, sorry, theta 1 is less than theta 2. It bends away from the normal like this. And this will happen to sound. And when we do light, we'll see it happens to light for completely different reasons. Here, the physics is this. Where does it start? It starts here. This is the physics of sound. The physics of light will be completely different. But the result is what waves do. This is the rules of waves. If I change medium, V changes, so F is constant, so lambda changes. This is for all waves. This is for sound. Sound is a wave, so it does this, so it does this. Light is a wave. We're going to see is completely different physics here, but it has the same result conceptually, right? But we have to be careful of where it's fast and where it's slow because it's completely different from sound. Anyway, there we go. So draw normal, ray meets normal, and then I will add a number 3 here. Sorry for jumping around, right? Theta 2 from Snell's law, which I'll give you in a second, or the concept. This is the concept. So, or concept analysis. Boom. So again, pause the video if you need to, but I'm going to move on. Snell's law comes from this drawing here. Sorry, this drawing here, where what we get is that we have a velocity v1, a velocity v2. We look at these two triangles here, we get that the sine of theta 1 over v1 equals the sine of theta 2 over v2 in this drawing. I will rewrite it again over here. Snell's law says no matter what the surface is, if I have a normal line and I have an incident angle, theta 1, we'll say it goes slower, pop quiz slower, is toward the normal line. Very good. Even at an angle, doesn't matter, right? See if you can tilt your head. Makes sense? Or it just makes sense on its own. Smaller angle, it goes through. Oh, wait, I forgot to say that, right? Theta 2 from Snell's law, right? The ray goes through the normal line, right? The ray goes through the normal. And I realize I'm getting a little excited, a little jumpy, but I think we can handle it. So theta 1 here, if it's coming from this side, goes through. Let's say this one gets bigger. And theta 1, it doesn't bounce off the normal line. It goes through the normal line, and this one would be even bigger like that. So theta 2, we'll say this is a faster medium. Theta 2. There you go. Make sure it goes through the normal, and you have theta 2 either going toward or away from it. That's it. Again, pause. Hope that makes sense. Draw normal to the boundary. Again, here's your theta 1. It goes through. It doesn't bounce off. It goes through. We'll say this is a faster medium. So this is faster. That means theta 2 is bigger than theta 1. It's bigger, no matter what geometry. Normal at the boundary. Boom. Theta 1 incident. Ray goes through the normal. Theta 2 on the other side. From Snell's law or conceptual analysis. There we go. So this is V1. This is V2. Sine of theta 1 over V1 equals sine of theta 2 over V2. Solve away. There's a secret that happens that you're going to find in your homework, and we'll talk about it on Monday. But there you guys go. Oh, wait, one more thing. Let's do a practice question. I'm just going to stick with the air bubble. So if we have an air bubble that's circular, so if I have a circular bubble, I almost did it. I did it in class. It's supposed to be a circle, right? Then the center, if I have a sound come in, say from the top, say I have sound come in like this. Well, this sound will hit at a normal line like this. This sound will hit, where's the normal line? Perpendicular to the surface. Here it's perpendicular to the surface. Here it's perpendicular to the surface, and so forth. All the way around. Take your time. This one is 90 degrees. This one we'll say is 60 degrees. This one is 30 degrees, right? What, and this one's also 90 degrees, and these are just symmetrical. These normal lines go to the center because it's a circle. if you draw a circle and you draw any line perpendicular to the surface, it'll go through the center. A radius is always perpendicular to the tangent line. Kind of cool, right? Anyway, so those will go toward the center. What do the refracted rays look like? I'll draw them in pink. Well, if this is air and this is water, this is like an air bubble. Air is 343. That's our V2. Water, V1, is 1466, right? Meters per second. Slower means smaller angle, which means it goes closer to the normal, closer to the normal. Even this one, if it got through, goes closer to the normal. Now, I did draw this somewhat accurately, and I assumed a huge change in angle because this is a relatively big change in velocity. What happens to this one? Theta 1 equals 0 means theta 2 equals 0, because the sine of 0 over V1 equals the sine of theta 2 over V2. You always get that theta 2 is 0 degrees. This is the trivial answer. So what are theta 2 for 30 degrees, 60 degrees, and 90 degrees? So if theta 1 is 30 degrees, then we set it up like this. Sine of 30 degrees, V1 is that's V1 is water, careful. V2 is air, 343. Sine of 30 over 1466 equals sine of theta 2 over 343. Careful that you have theta 1 lined up with V1 from the picture. Take a look at the picture. Do I have it? Theta 1 is 30. V1 is where it's coming from. That's water. Water, velocity of water, theta 1. Take a second, look at it all. Cool, I got it. Water, water, air, air. Water, water, air, air. That second, that breath, just that clarity. Focus your eyes. Water, water, air, air. Water, water, air, water. And then the air, the air. Okay, cool. That alignment will help ground you. Write your information. I'm telling you guys, this makes a huge difference. Write your information. Plug it in. Make sure it's aligned. Great. And then what we would get is we would do the theta 2 is the inverse sine of some decimal that you would find. And you would get that it should be 6.7 degrees. That's tiny. And for theta 1 is 60 degrees. I think you should get theta 2 is 11. We just did it behind us. We get 11.7. And when theta 1 is 90 degrees, we get that theta 2 is 13.5. And that's interesting. You're going to think about that for your homework. This is 13.5 degrees. This is 11.7 degrees. This is 6.7 degrees. That's your math. That's your answers. That's your drawing. These will go all the way through. They're converged to the center. They'll come out in a weird way, but they're converged to the center. It's like a converging lens. It's a converging sound lens. Kind of cool. Kind of trippy. I like it. I hope you guys dig it too. One last point. This is cool. If I would have the sound somehow originate in the air and go to the water, it would come out at 90 degrees. And what if I made this bigger? Then this couldn't leave the air. It would have to. Interesting. What would happen then? I'll let you to think about it. Oh, one more thing. Ready? Want to see a video of wavefronts? Video Thursday, but here it is. Ready? Video of wavefronts. Ooh. Ah. Which one's slow? Oops. Which one's slow? Which one's fast? Slow. You see how this one's slow? Slower wavelength. But you see how the compression causes a compression? So fast would be water and air. Water and air. So the compression causes a compression here. The compression here causes a compression in the air. Water, air, water, air. I don't know what these dots mean in this video. But do you guys see how the wavelengths are farther apart here? And to line up, they have to Yep, there's another one. They have to get shorter, so they have to bend. Now, this one was what? Faster to slower. So it went from this angle to this angle. And if they go from slower to faster, they bend outward, right? Smaller angle to larger angle. And that is it. And this guy's talking about it in terms of light, but he made a sound lens. So it's kind of cool. We'll do light eventually, but the point is it works for sound, which is kind of cool. Bye, guys. See you in class.